Chapter 6 is all about normal distributions. So now the word distribution means something to you guys, right? Because we had probability distributions, right? And not only did we have probability distributions, we could draw a histogram with them. I don't think I did that on the quiz at all, but we can. But if you draw a normal distribution, what does it look like? Something like one of these. In other words, it's not a parabola. It's a bell curve, we say. And the reason it's different than a parabola, for those of you that know that algebra, a parabola will go down forever. But a bell curve or a normal distribution never gets lower than the x-axis. It flattens out and goes infinitely this way. Matter of fact, Dylan, since you brought it up, I do like to mention this fact. This is the x-axis, right? Let's show it a little bit better than that. When you have a normal distribution, okay, the bell curve, you have some real nice symmetry, right? But the other thing you get is the curve gets closer and closer and closer to the x-axis, but it never hits it. That has a name in algebra. Does anyone know? Have you've heard that word, asymptote? Yeah, the x-axis is an asymptote. And I don't know that the book says that, and I don't need you to know that, but if you've had enough algebra that you've heard that, it's kind of nice to understand. Because wait a minute, when we studied probabilities, actually it was just in this quiz, this chapter, chapter 5, right? We said for a probability distribution, there were two important properties, right? One of them was that the probability had to be between two numbers. Has to be greater than what?
Greater than 0.
Greater than 0, greater than or equal to 0, and less than or equal to 1. You can't have a probability higher than 1. You can't have it. So when you look at this graph, and I tell you that the brown curve is never going to hit 0 or never go below 0, that should make you happy. Because you see, oh, okay, maybe this has something to do with probability distributions. Now the difference between chapter 5 and chapter 6, in chapter 5, you have discrete probability distribution. In chapter 6, what do you think I'm going to say? It's a continuous probability distribution. So, again, and this was on your quiz, right? Discrete, you can't hit every single number, but continuous you can, right? You can have 3.4 and it'll show up on a graph like this bell curve. Okay? Every number on the number line is fair game when it's continuous. Not discrete. And actually there was one other requirement besides the inequality. And it had to do with if you added up the probabilities, right? Where you add them up over all the x's, right? What happens if you add all the probabilities in a probability distribution? It has to add up to what? 1. Right? We use that fact a lot. Matter of fact, on your quiz, did anyone do... There was a problem where I asked you to find the probability that there are, was it 13 or greater or something like that, or 2 or greater? I don't know. I listed a whole bunch, like 14 different possibilities, and you had a whole bunch of probabilities, right? And we talked about that sometimes the easier way to do it is to use the complement, right? You could do 1 minus a very small number of things, right? That's all because the probabilities always add up to 1.
But it's not up to 1.
It didn't because of rounding error. What did it add up to?
0.999.
So it was really close.
Yeah.
Yeah, that's because of rounding error.
Okay.
Yeah, it's a little worrisome at first, right? If we had done another decimal place, we probably would have been okay. Yeah, that's interesting. Good observation, Laura. It added up to 0.999, and Laura's giving me a hard time. That's cool. Well, the continuous probability distribution, the issue is you can't add all the x's. You know why? Why can't you add all the x's for a continuous? Well, see, if I wanted to add all the probabilities like Laura did on the quiz, I would have added the probability of being 0, 1, 2, 3, I think it went up to 14. So Laura, in her spare time, added all those up and got 0.999, right? What if it's continuous? Why can't you do that? Because how many different x values are there? Infinitely many. Are you with me? So what do you do instead? There are two possibilities. Either use calculus. We're not doing that in this class, guys. Or, here's what we're going to do. We're going to have an understanding that area is probability. If you understand this, that's the basic idea, is that in a continuous probability distribution, area equals probability. And I need to demonstrate that with a problem. So let's solve a problem. Actually, it's funny because I can't believe I'm doing this now because, was it 2 nights ago? I walk in the house and my son and my wife are there watching a movie from a number of years back now, but my son had never seen it. You ever heard of the movie Armageddon? So what's the premise?
Bruce Willis on an asteroid.
Bruce Willis, no, the asteroid, right?
That's the asteroid.
So actually it's a comet headed right for Earth, right? And so he has to go up there and destroy the comet somehow before it destroys us, right? So classic movie. Well, no, not classic movie. I was kind of like, all right, whatever. But it ties into what I wanted to do here, which is the following problem. Okay? Here's the problem. If a meteor strikes a point on the surface of the Earth at random, by the way, there's the key word. What is the probability that it strikes water? Right? I mean, if it doesn't hit land, that's a better sign for Bruce Willis and the rest of us, right? So how do you answer this question? You Google. Yes, that's right. What do you Google?
What percentage of the Earth is covered by water?
Well, there we go. Does anyone know, by the way, before I finish my little Google search?
70-something?
I thought it was like 78.
I remember learning things like 75. I remember learning 80. Here, I got Google. Let's just say percentage of Earth. Am I there yet? Is it guessing what I want? There we go. Percentage of the world covered in water is 71%, so they say, right? So, back to our problem. What's the probability that it strikes water? Is that true? Is it true? I guess it is if you believe that area equals probability. And if you believe, here's the other key thing. I said at random. What does that word random mean? All points, yes, equally likely. Now, the scientist in me would say, is that really true? Is it really true that the Earth, all points are equally likely to be struck?
No, because it's three-dimensional, not two-dimensional.
Well, it is three-dimensional. But here's the next question. Can meteors come from any direction in 3 dimensions? And I would need to know more than I do now to answer that question. But I will say this. I do know that our solar system tends to be... You guys know what the planet Saturn looks like? Well, it has rings, right, that go out and stay really flat. And solar systems tend to look like that. So do galaxies, by the way. Which makes me think that the equator might be more likely to be struck than other parts of the Earth. So interesting, I think. But beyond the scope of this class. The whole point was trying to demonstrate that it's very natural for us to think of area being probability, right? Here's another problem that I think is a classic problem. So my son Stephen, when he goes to high school, he often takes the rapid, okay? Because we live walking distance from the rapid transit, all right? So in Shaker Heights, where I live. And so he'll walk there and then take... But here's a problem, okay? So I guess I'll honor my son here. So Stephen has no idea about the rapid schedule, the RTA rapid schedule. Except that on weekends, trains come every 30 minutes. Let's zoom out a little bit here. Okay, so here's the question. Stephen goes to the rapid stop. Find the probability that Stephen waits for more than 10 minutes. It's not hard. I'm going to pause and just see what you guys do with that. You can talk to someone near you about it for a minute. That'd be a worthwhile exercise, I think. A line here, right? And we want to measure, say, that area, right? Oh. This thing is not being nice to me right now. I can sneak it through. There we go. The total area, and this is a key idea, right, is that the total area always has to equal what? 1. The total area equals 1. And by the way, if this is a rectangle with a length of 30, I guess the height of this rectangle must be 1 over 30. Because 30 times 1 over 30 is 1. Okay? So now my question is, the rectangle that I shaded, what's its area? Its area is 1 over 30 times Well, how long is it? It's 30 minus 10, right? So that's 1 over 30 times 20. Okay? So we get 20 over 30, which is 2 out of 3. Oh, which is what percent chance, by the way? 0.6, repeating. Okay, so you could say about 67% chance.
Sorry.
Yeah.
I got lost after that.
So the 1 out of 30 is what threw you, right? Maybe this is the easiest way to say it. Okay? How much of this area, how much of this rectangle is greater than 10 minutes? See? 1/3 is less than 10 minutes, 1/3 between 10 and 20, 1/3 between 20 and 30. So it's funny, I calculated using numbers, but honestly, you could see that 2/3 of the rectangle is colored in.
Okay.
So the probability is 2/3. Now, for homework, we're going to get a problem like this. Look at number 10. Number 10. And I'll even zoom in a little bit so you can see. When we use the normal distribution, you will see that instead of using an x-axis, we're going to use z. And that's because we're going to see on Monday what we're really talking about in the standard normal distribution are z-scores. We're talking about z-scores. But all we're supposed to do here is find certain probabilities. Okay? And I will show you how to do it on an Excel. I'll show you how to do it plenty of ways. But I thought today, let's at least give you one method. Let's use the calculator and show you how to compute that area, which is also a probability. So here's the picture. It says z equals negative z equals negative 1.04. That was the line that they drew. And by the way, it's kind of nice to know that the z-score that's right in the middle is 0. The book doesn't write that always. But the picture for number 10 looks like this. And we're supposed to find this area. Once again, the total area is 1. So this is going to be a portion of it. It's kind of like the Stephen problem we did. It's just that it's a bell curve instead of a uniform distribution. You guys with me? Now, this problem ends up being so important in statistics that the calculators make it the very first choice when you guys punch up distributions. Do you remember how you do distributions? You hit the second key, this blue one, and then what? Oh, wait, here, let me get out of the graphing stuff. This may be confusing people, sorry. Okay, let me just go back to good old home screen. Okay, so if I want to do, let me clear out. If I want to do this, I hit the second key, and then I hit this distribution was right here, VARS, right? And do you see the very first thing it lists is normal PDF? That's not what you want. You want to go down one. What does the C mean in normal CDF? Cumulative. And see, we want area. We want to add stuff up. So I'm going to do normal CDF. It says, what's my lower bound? And by the way, that means really, really low. -1 times 10 to the 99th. That's not what I want, though. I want, what was my number? Negative 1.04. That's what I want for my lower bound. Now my upper bound, I need something huge, way off to the right. Guys, put a really big number. How about 1,000? Leave the mean and standard deviation the way they are, 0 and 1. And this will give you that area. Normal CDF is how you find the area. 85% of the area is in this picture. And of course, 85% also corresponds not only to area, but also what? Probability. That's it for today, guys. That's enough to get you through that homework, I think.